couple of things. I will periodically make announcements that I'll publish on the Learning Suite page. So just look at the course page for Learning Suite for various announcements. Yesterday, there were a few people that had some questions about wave functions and operators. I made a couple of videos about them that I posted on YouTube, and the links are on the content section of Learning Suite. I will just say that I'm not going to ask you to derive anything math-wise. The qualitative conclusions are the important part. And what we talked about last time was that you can we talked about bonding in hydrogen, and that you can make a bond by overlapping a 1s orbital from one hydrogen with a 1s orbital from the other hydrogen to create a new sigma bonding orbital. And we talked about how in this orbital, most of the electron density would be between the two atoms, and that would tend to pull the atoms together. We also talked about how the bonding orbital has a shallower slope that doesn't change quite as much, and therefore electrons in that bonding orbital are more spread out and have more have less kinetic energy, so they're lower in energy. We talked about how the math of MO theory makes you, when you're combining wave functions, consider both the plus combination and the minus combination. And in the minus combination, the fact that you've got two different mathematical signs of the wave function means that as you bring them together, they cancel out at one point. And along this line in the middle, wave function equals 0, which means wave function squared equals 0. We call wave function squared electron density, or in other words, probability of finding the electron at that point. So if we were to fill this anti-bonding orbital, it would have the electron density would be 0 along this node in between the two atoms. And it turns out that both lobes on either side of this node tend to be oriented away from the space between the two atoms, so that if you filled that orbital, it would tend to pull the atoms apart. We've talked about how this is a bonding orbital. A term I think maybe I introduced last time is that we will call it a sigma bonding orbital. The sigma is a term we're going to use for end-on-end overlap of orbitals. And one interesting feature of sigma orbitals is you can twist one partner relative to the other, and end-on-end overlap doesn't change. Similarly, we're going to call the anti-bonding orbital the sigma star. The last thing that we said was that the anti-bonding orbital is destabilized relative to the bonding orbital. You can tell because it's got a node, right? And we talked about how it's even higher above your break-even line, your sort of starting level of the atomic orbitals, than the bonding orbital is below. So this distance delta EAB is actually bigger than this distance delta EB, which means if you promoted an electron from bonding to anti-bonding orbital, you'd cancel out the benefit of having the bond and you would break the bond. I'll point out that the stability you get by taking an electron from an atomic orbital and moving it down into this bonding orbital is a per electron kind of stability. So I don't know, suppose it's like 2 stability units to go from here to here. You've got 4 units overall of stability, 2 for each electron, all right? And then suppose that this distance here was like 3 stability units. If you promote 1 electron up there, you're destabilized by 3, stabilized by 2 for the remaining 1, overall lack of stability, and the molecule breaks. Anything more we need to say about that? Okay. Turns out for hydrogen, the valence bond theory picture and the MO theory picture are basically the same. The insight from MO theory is that we have this empty anti-bonding orbital that we need to consider. Now, I mentioned last time that MO theory loses the focus on individual pairs of electrons shared between atoms, and instead considers molecular orbitals that are delocalized over the whole molecule. Of course, in hydrogen, that's sort of one and the same thing. There's only 2 atoms in hydrogen. But if we get a little bit more complicated, methane, this other simple organic molecule, I want to just show you briefly how the MO picture deals with methane. And in doing this, I don't want to overwhelm you because I don't expect you to be able to derive these MOs on your own, but I want you to see where the conclusions of MO theory come from. Before we begin, I'll just remind you that in Lewis structures, solid lines represent pairs of electrons shared between atoms. And if the line is a wedge, that means that bond is coming out at you. If it's a dash, it's going back into the page. You need to get, so you look at that and you think, oh, that's a tetrahedral carbon. It's sp3 hybridized. It has a tetrahedral shape. All the bond angles are 109.5 or so on. Okay, in the valence bond approach, we would say each of these bonds comes from overlap of an sp3 hybridized orbital from carbon with an s orbital on hydrogen, right? And we could even draw that. Oh, there's the sp3 orbital on carbon. We would add it to the s orbital on hydrogen. And once we did that, we would get a new bonding orbital that would envelop the hydrogen and have a lobe of opposite phase, small lobe on the other side of the carbon. And there would be 4 of those. With the pure MO picture, though, we're going to actually not even worry about hybridization at all. We're going to think about what the available atomic orbitals are from each of the atoms in methane. So we have 4 1s orbitals, 1 from each hydrogen. And then on carbon, we would have a 2s orbital, and then a 2px, 2py, and 2pz. So I've got 8 atomic orbitals overall that I can combine. And the first rule of MO theory that's mentioned, well, actually, I guess it's the second that's mentioned in your study guide, is when we mix these together, we have to get out the same number of molecular orbitals. Okay, so 8 orbitals in, we're going to need to make 8 molecular orbitals. All right. And these molecular orbitals are going to be delocalized across the whole molecule of methane. All right. We build the first one by adding together the 4 1s atomic orbitals on each hydrogen with the 2s orbital on carbon. What's that going to look like? Well, I'll show you sort of the idea. I'm going to draw each of those individual atomic orbitals so that you can see where the new orbital we're going to get comes from. This is the 2s orbital from carbon, and then each of the 1s orbitals from hydrogen. But what I mean by this actually is that when you mix them together, here's what you get. I'm going to no longer show lines between the atoms, but you can see they're still arranged in the same way, so they still have this tetrahedral arrangement. The orbital we make from all of that is a single molecular orbital that encompasses all of those atoms. All right. And let me just take a second to show you a 3D turnable image of what this orbital looks like. There's a program called Spartan that I have on my iPad. Recording stopped. That's really bad, isn't it? Oh, well. Sorry, folks. I don't know why the recording stopped. Let me just...
I don't think it was the Zoom recording.
Maybe we're out of memory. That could be bad. This is an app that allows me to, how do I, yes. This is an app that will give me, yeah, okay. Stupid iPad. No, it's not the iPad's fault. It's actually running out of memory on the laptop. Oh, well, that's all right. Zoom is still recording, so I think we're all okay. Sorry. One of these days. There we are. Okay, so you can see it up there, and folks at home, I think, are still, screen sharing is paused. Stop share, restart share. Okay, are we good now? Sorry, technical difficulties. While we're paused, Wallace, we got anything on the chat? No, okay. So I'm going to draw methane here, and then there's our molecule of methane, and it will actually allow us to see the molecular orbitals of methane. So that's what the first one looks like. It's a delocalized orbital that envelops the whole molecule. Okay. Questions you want to ask so far about where we get that from? Yeah.
In that orbital, there's more probable spots for electrons to be, so to speak.
That's right. They are spread out over a larger space. The key difference here is this orbital can only contain 2 electrons. So instead of thinking, oh, hey, that bond is 2 electrons in a bonding orbital between carbon and hydrogen, we can think of it another way and say, oh, actually, there's a low energy pair of electrons that are delocalized over the whole thing. Which bond are they associated with? And the response is for the MO theory people to sort of look at you quizzically, tilt their heads, maybe squint their eyes and say, what is this bond you speak of? In MO theory, you lose the focus on bonds, but you retain the focus on molecular structure. And instead, you have electrons that are delocalized. I want to show you how we use one of the p orbitals to make another MO for methane. It's not crazy important, but I want to show how MO theory has a solution for methane that doesn't depend on orbital hybridization at all. But I want to make one thing clear. I think people sometimes look at my drawing of where this orbital comes from and think, oh, there are 5 orbitals there. We've already used 5 of our 8. This is one of our 8 combinations of orbitals. We've only made 1 molecular orbital so far. Is that good? Okay. So for the next combination, and there will be 2 others that are exactly like it, only oriented a little bit differently. I'm going to erase the 2s orbital, and I'm going to switch the phase of these 1s orbitals on hydrogen at the bottom. And then I'm going to draw a p orbital. It's going to be this lobe of the p orbital on carbon is going to be pointed out in the plane of the page toward these two hydrogens. So this p orbital juts out into the space between those two hydrogens. It's in the plane of the page, and it will overlap in phase. So there's a bonding interaction there. You've got in phase constructive overlap between the hydrogen, the carbon, and the other hydrogen. And then on the other side, we're going to have the other lobe of the p orbital also in the plane of the page, and also sort of bisecting those two hydrogens, the one that's coming out and the other that's going back, so that that lobe of the p orbital can overlap in phase. If we were to try to draw what this looked like, oops, I didn't want to cut, I wanted to paste. There we go. Here's our tetrahedral array of hydrogens around a carbon. We would have one sort of hot dog shaped lobe that would envelop the two hydrogens. So there'd be a node at the carbon. And then there would be another lobe of similar size, but oriented differently, right? This one would be going back into the page and then sort of coming out of the page at us. It's almost like you got two lobes and they're oriented sort of 90 degrees relative to each other. And this is one of the other bonding orbitals for methane. Just so you can get an idea of what that looks like, I'm going to switch back to Spartan. We'll look at the MOs again. Here is the lowest energy one that we already drew. And then here is one of the ones I was just telling you about. You see how the blue lobe is crisscrossed with the red one? That's sort of the structure that we have. And there are three of them because I have three p orbitals oriented at 90 degrees relative to each other. And so suppose this is the 2px orbital. I can do this same thing with the 2py oriented in another direction and the 2pz oriented in another direction. So we might call this one 2px from carbon plus 1s from one hydrogen plus another 1s minus a 1s and minus a 1s. That is a unique combination, and it can be filled with two electrons. Remember, in orbitals where we switch phase, the electrons are in both areas simultaneously. The phase just means mathematical sign of the wave function. It's positive here, negative here, and 0 there, but the electron encompasses all of it. So the MO picture for methane tells you, let's see, and that you have, well, actually, let me go here. I'll show you the other two, and you can see they come from the same sort of arrangement, but only we're changing the p orbital that's in the middle. Any questions so far? Yeah. Okay. When I say in phase, I mean you bring two wave functions together and add them. That's like bringing the 1s orbital to the 1s orbital and you add them. The out of phase is you subtract them. Yeah. Okay, if you were to look at these two orbitals, which one, I mean, I've already sort of shown you the answer. Fine. This one is the higher one. How do you know that? Because I just said so. Okay, fine. But what if I wasn't here? How do you know that that's the higher one? Go ahead.
Because the out of phase ones take more energy.
Yeah, the more nodes you have, the higher in energy it is. Think back to the slinky. The more I was sort of going crazy, jiggling, trying to make the wave have more nodes. Hold on. The harder I worked, the more nodes the slinky had. Similarly, the more nodes an orbital has in general, the higher in energy it is. So yeah, we would say this is our lowest energy molecular orbital, and then this is higher. And if you look at that diagram from Spartan again, you see that MO theory predicts we have one lower in energy pair of electrons and then three higher in energy pairs of electrons, all delocalized across the whole molecule. This is a different picture than we got from valence bond theory, where we would say, oh, methane has 4 identical CH bonds. 2 electrons shared between each carbon and hydrogen, and between the carbon and each hydrogen. Which picture is right? Well, it turns out you can observe this energy difference shown here between the between these higher energy orbitals and the lower energy orbital in a particular kind of experiment. But it will turn out, for most purposes in chemistry, we're going to be just fine thinking about sigma bonds as being localized between 2 atoms. All right. So for methane, even though there's this more complicated picture out there, we're going to be okay looking at methane and thinking, okay, we've got 4 carbon hydrogen sigma bonding orbitals that we get from overlap of an sp3 on carbon with a 1s on hydrogen. And then we're also going to have 4 anti-bonding orbitals that are higher in energy, for 1 for each carbon hydrogen bond. And we would even be fine drawing some energy diagram where the bonding orbitals were down here, the anti-bonding orbitals were up here, and we said the bonding orbitals are filled with electrons and they're all the same energy, even though that's not quite what experiments say. Yeah.
How would this look differently if you had lone pairs?
How would it look differently if we had lone pairs? Lone pairs are in non-bonding orbitals, so those would tend to be in between the anti-bonding and the bonding orbitals. And I'll show you some examples of that soon. All right. So for us, instead of being dyed-in-the-wool valence bond theory people or extremist molecular orbital theory people, we're going to take a hybrid approach. And we're going to use concepts from valence bond theory where they are useful. We're going to use concepts from MO theory where they're useful. We're going to retain the focus on sigma bonds as being electron pairs shared between atoms. But we're going to remember that each sigma bond should have an empty high energy anti-bonding orbital associated with it. Now, the place where MO theory is going to be really great for us has to do with resonance. But before I go there, anything else you want to ask about what we've done so far? Yes.
Is it possible for, in the case of methane, to have only one of the hydrogen atoms be out of phase? And if so, would that claim?
Okay. So the question is, I could, is it possible for me to draw an orbital where only one of those methanes would be out of phase? It seems like a legitimate combination. It turns out that doesn't come out of the math if you do the analysis. And I have a hard time explaining why, other than to say, well, there's this rule, which really just reflects what the math tells you. And the rule is that the orbitals you get have to be either symmetric or something called anti-symmetric with respect to the molecule. So let me show you what I mean by that. And it's easier to see if we're looking at the orbital. This orbital is symmetric with respect to the molecule. I'm going to turn off the orbital and we're going to look down a carbon-hydrogen bond at methane. And we're going to see that there's going down into the page, there's this threefold axis of symmetry. If I rotate the image, and I don't think it wants to let me rotate the image, and if I do it here, you don't see it on the screen. But if I twist that image around 120 degrees, it's the same thing, right? Similarly, if I twist this orbital around 120 degrees, it's the same thing. That orbital is symmetric relative to the molecule. How about this orbital? Well, if you look at methane, it has a weird symmetry operation where if I take, well, the anti-symmetric part tells you it's got to look symmetric, only the phase switches. And so if you were to just take one of those 1s orbitals, it wouldn't agree with that rule, which comes out of the math and which you're not really going to need to know. Yeah.
Thank you.
Yeah. What else? Okay. So let's talk resonance. Resonance is a valence bond theory concept, and it comes because of the discovery that some molecules have multiple possible Lewis structures. So here's a molecule which I'm going to fill in a few of the carbon-hydrogen bonds that are implied but not usually shown. And we're going to put a lone pair on that carbon with a negative charge. And we're going to call this carbon 1, 2, and 3. That is a Lewis structure for a molecule which happens to be called allyl anion. Okay. And one of the interesting things about this structure is by simply rearranging the electrons involved in the double bond and in the lone pair, we can draw a new Lewis structure. There are rules for generating resonance structures. They are given in your introductory study guide. I think you have some experience with resonance structures from Gen Chem, so I've decided to abbreviate that and what we're going to talk about in class. If you struggle with drawing resonance structures, you really should fix that because it will be important going forward. Okay, resonance tells you that the electrons in this pi bond, the second bond of the double bond, are delocalized between carbons 1 and 2 and between 2 and 3 simultaneously. Resonance structures do not represent equilibrium points that you're jumping back and forth between. It's not that the double bond used to be here and then we switch over and it's there and it's going back and forth really rapidly. When resonance structures are possible for a Lewis structure, it tells you that the molecule is more complicated than you can represent with just one Lewis structure, and that the real structure is actually probably a combination of them. In the case of the allyl anion, if we were to draw what this molecule really is doing, we would see that a pair of electrons were delocalized between carbons 1 and 3, and I'm using this weird dotted line just to indicate that there's partial double bond character between 1 and 2, and also between 2 and 3. And then I would also indicate that there's about half of a negative charge on carbon 1 and about half of a negative charge on carbon 3, but never on carbon 2. Is that good enough of a resonance review? All right. Let me test your resonance understanding by asking you, what is the hybridization of carbon number 3? Somebody said sp2. Saw a hand. Yeah, is that, or what do you think? That's what you're going to say too? Good. sp2, you've successfully evaded my carefully laid trap. Probably either because you figured it out here or because you read the answer in the study guide, which is good. How do you know it's sp2? Carbon 3 is sp2. What if I said, well, there are 4 groups around that carbon, so why isn't it tetrahedral sp3? Yeah, go ahead.
Because I mean, you have like 4 groups, but then like those 2 electrons are sort of bonded to anything. So when you look at like hybridization,
Okay. So one potential explanation, I'll just, for the folks at home, I'll just paraphrase what was just said. The lone pair isn't bonded to anything. And so maybe that means you don't need to consider it in hybridization. What about ammonia that has trigonal planar structure? In that case, we do treat the lone pair as if it were one of the groups. Okay, so it's a reasonable suggestion, though that actually turns out not to be the reason. What do you think?
Just because the electrons are delocalized, so it's like, I think I read it, so you wrote in your study guide, like, because carbon 1 has an sp2, carbon 3 also has an sp2.
Okay. Right, and you don't need to apologize for reading the study guide ahead of time. Spoiler alert, I read the study guide. That's a good problem to have. In fact, these lectures will go better for you if you spend a little bit of time in the study guide ahead of time. Yeah, so in the structure on the right, carbon 3 is involved in a double bond, therefore it's sp2, it's trigonal planar. If it's sp2 in one resonance structure, it must be sp2 in the others, because resonance does not involve moving atoms, only electrons. If you move atoms, you have not made a resonance structure, you've made a new molecule or a structure that might be in equilibrium. So if it's sp2 over here, got to be sp2 over there. Yeah.
Which atoms would move if we were to say that?
If you were going to say that thing was switching between sp2 and sp3, the hydrogens and the other carbons, so this one, and this one, those would have to shift downward and pop the middle carbon up. Yeah. All right. So if we were going to take a valence bond theory approach, we would say the pi bond between 1 and 2 comes from which atomic orbitals? The 2p orbitals, right? And that's side to side overlap to create a pi bond, right? And actually what this would look like is a lobe above the plane where the pi bond lies, and then a lobe below the plane spanning both atoms, okay? And that, I think pi bonds are dealt with a little bit in the introductory study guide and maybe again in the MO theory study guide. Does that look familiar to you? Okay. If carbon 3 is sp3 hybridized, what kind of atomic orbital would that lone pair be in? Sorry. Sometimes I say things that are different from what's going on in my mind. If carbon 3 is sp2 hybridized and trigonal planar, what atomic orbital holds that lone pair? The only one you got left, right? The p orbital, the 2p z orbital. So I have on carbons 1 and 2, I've got p orbitals, and on carbon 3, I have another p orbital. All right. So even from the valence bond picture, it should be clear to you that you have a p orbital on each of those carbons in a row. All right. And in valence bond theory, we don't really worry about what the orbitals are. We just look at both resonance structures and then we interpret what that hybrid structure must be. In the MO picture, we're going to actually think about what happens when you try to line up 3 p orbitals together. All right. But before we do that, I need to make a point, which is this allyl anion is trigonal planar. All of the sigma bonds lie in the plane that I'm drawing here, whereas the p orbitals that we've just talked about are above and below the plane that we've drawn there. Orbitals that are 90 degrees away from each other don't interact or mix. So what this means is we can think about what's going on with those p orbitals above and below the plane without worrying about the sigma bonds that are in the plane. And this is a useful simplification. So instead of having to think about what happens when you take orbitals from all however many of those atoms there are in that molecule. We simplify it. We say, okay, we know sigma bonds. They're sort of boring. Let's think about the remaining p orbitals that are on each of those carbons coming in and out of the plane. Okay, so according to MO theory, you're going to take the 3 orbitals and add them together to get 3 new MOs out. And the easiest way to see where this comes from is to start. I'm going to use dots here to indicate the positions of carbons 1, 2, and 3. And we're going to start with 2. We'll mix those together, and then we're going to add in the 3rd. Okay? So, and I'm just because I want to, and because it's a little bit clearer this way, I'm going to say, let's add the 2p orbital on carbon 1 with the 2p orbital on carbon 3 in phase. That'll be the plus combination. If we were to name this orbital, I suppose we could call it 2p from carbon 1 plus 2p from carbon 3. And then we would need to, at the same time, deal with the out of phase combination, where we subtract one from the other. And this would be the minus combination, or the destructive interference combination. Okay, easy enough so far? You got those 2 possibilities. And both of them happen to satisfy this symmetry rule that we've talked about before. The plus combination is symmetric. The minus combination is anti-symmetric. It looks like it's symmetric, only the wave function signs are opposite on either side. Okay, so we got those 2 options. Now we're going to add in the 3rd. We're going to add in the 3rd orbital, the one from carbon 2. So let's imagine that we now take this combination, the 2p1 plus 2p3, and we're going to add and then subtract the 2p from carbon 2. We're going to think about the in phase versus the out of phase combination there. All right, well, here's atoms 1, 2, and 3. The in phase combination, where we would take the 2p1 plus 2p3 and then add the 2p2, should look like this. We'll show all 3 of those orbitals lining up. I think I changed where stuff was, doesn't matter, but okay. And actually what this orbital would look like is one continuous lobe spaced out over the whole area above and below the plane of our molecule. I draw those individual p orbitals just to remind you where this comes from, and there are 3 different atoms. What do you suppose the minus combination should look like? 2p1 plus 2p3 minus 2p2. Okay, you tell me where to, what colors to fill in where. Yep. Would the middle one be flipped? The answer is yeah. Because we've taken just this same one that we started with, and instead of adding the middle one in phase, we've flipped it. We're subtracting it. Okay. Oh, no. It just ruined physics. All right. Let's compare those 2. Both of these orbitals has a node in the plane of the carbon atoms. Other than that, does the one on the left have any other nodes? No. Okay. And the electrons, if they were in that orbital, they would tend to be delocalized all over carbons 1, 2, and 3 and between, in the space between them. We're going to predict that this is a bonding orbital because you've got electron density between atoms. How many nodes do you see in this orbital on the right, this out of phase combination? Other than the one that's horizontal. 2, one here and one there. Okay, if you said 4, the node on the bottom is actually the same as the node on the top. And in this orbital, there's no electron density in between the atoms. And so this is going to be an anti-bonding orbital. Okay, 0 nodes, 2 nodes. The word node is funny. My kids have all outgrown their various speech issues, but some of the words have been retained in our family. One of their kids, one of my wife's brothers, always used to show up at our house and say, "Hey, nerds," to my boys. But when you're young, you can't say your R's very well. And so nerds, if they returned it back to him, would sound like node. And so whenever I write nodes, I think of nodes. Hey, nodes. Anyway, sorry. I will periodically throw in stupid things about my life, and it will help me a lot if you can laugh at me. You don't have to laugh with me. I won't be able to tell the difference, actually, if you're laughing with versus at me. So what about, okay, now we need to think about the plus minus combination of the 2p2 orbital with this other one. Okay. And it turns out that in the original 2p1 minus 2p3 orbital, we have a node, another node, that coincides with carbon 2. 0 electron density along carbon 2. And what that means is it actually doesn't matter. We actually can't mix in the 2p2 orbital there because there's already a node there and it would go to 0. So mixing in that 2p from carbon 2 makes no difference at all. So this becomes our third molecular orbital that we were missing. Notice that this orbital has 1 node, singular, and notice that there's no electron density between the atoms, but there's also no adjacent switch in phase. And this will turn out to actually be a non-bonding orbital. You can tell bonding from non-bonding orbitals because bonding orbitals have same wave function sign on adjacent atoms, whereas anti-bonding orbitals have opposite wave function sign on adjacent atoms. And then non-bonding orbitals don't have same or opposite sign on adjacent atoms. One of the atoms has 0 electron density on it. Okay. Now, that's the process of generating these 3 molecular orbitals. I'm not going to make you do that, but I will expect you to be able to look at molecular orbitals of this kind, count the nodes, figure out which one is lower in energy versus higher in energy, and then fill them up with the available electrons. So let's just, to simplify things, all of these orbitals involve side-by-side alignment. So we'll call them pi orbitals. Which one do you think is lowest in energy? Bottom one, we'll call that pi 1. Then of the remaining 2, which is lower? Top one, the non-bonding one, is pi 2, and we'll call this pi 3. It's as easy as counting nodes. The lowest energy one is the one with no vertical nodes, and then count up from there. So we could make an energy diagram And I'm not going to redraw these pi orbitals. Actually, I probably will, but we'll just go pi 1. Here's our break even line, or our non-bonding line. That's where pi 2 should be, because it's a non-bonding orbital. And then up here is pi 3. Now, I'm going to redraw one of the resonance structures for our allyl anion. How many electrons were involved in resonance? Do you remember? How many move? 4, right? So I'm going to fill the available molecular orbitals. I'm going to fill the molecular orbitals with the available electrons, starting at the lowest energy orbital, 2 per orbital opposite spin until I run out. Okay. So that means we've got 2 electrons here and 2 electrons there. At this stage, I'm going to introduce a new term. The lowest unoccupied molecular orbital is going to be called the LUMO. And I'm not going to write out the rest of the words because I'm lazy. And the highest occupied molecular orbital we'll call the HOMO. The HOMO and the LUMO. The HOMO is the highest energy electrons, the most reactive electrons. The LUMO is the lowest energy hole for more electrons to go into if we added them. All right. So I'll zoom out just a little bit. We talked about how the structure of allyl anion, according to valence bond theory, was probably more like this hybrid structure. Okay. So I want you to tell me, I'm going to copy some of these pi orbitals that we've dealt with. And I want you to look at the pi orbitals and look at the hybrid structure from valence bond theory. And I want you to think about whether they agree. All right, that's pi 1, this is pi 2, this is pi 3. Okay. So according to our resonance structure, we said there were electrons that are shared across atoms 1, 2, and 3 in the valence bond picture. What does the MO picture tell us? Which one of those MOs reflects that expectation? Pi 1, right? Bonding electrons in an orbital that extends over 1, 2, and 3. Okay. So at least in that way, the resonance picture gets us to, from valence bond theory, gets us to the same place that MO theory gets us. Now, how about the observation that the negative charge can be on carbon 1 or 2, I'm sorry, 1 or 3, but never 2. We've got partial negative charge on 3, partial on 1, none on 2. Which of my MOs accounts for that? Pi 2, right? Because if I put electrons in pi 2, they would be delocalized on 1 and on 3 with a node on carbon 2. They can never be on carbon 2. Poor carbon 2 all by itself, and the pi 2 electrons can never reach carbon 2. Well, sorry, that's just the way it works. And here's the even cooler thing. The MO theory picture tells you that the most reactive electrons are the ones that are on carbons 1 and 3. And that's exactly what you would expect from resonance, where you got the negative charge on carbons 1 and 3. All right. So therefore what? As we move forward, we're going to retain our focus on sigma bonds as being between 2 atoms. But when we have opportunities for resonance, we're going to need to take a step back and account for the existence of these extended pi orbitals where I have multiple atoms in a row sharing pairs of electrons across them. Okay. Next time I'm gonna need to push back the due date on this MO study guide. Next time we're gonna learn to identify HOMO and LUMO in any kind of organic molecule. Have a good day and we'll see you next time. So long, folks.